Hey guys, this is a full version of my recent interview with Sean Carroll. It had been only available to Patreon members, but I decided to release it to the general public for two reasons. It's not only to celebrate the milestone of 200,000 subscribers recently, for which I'm very humbled, but also because I feel it would be an injustice not to share this valuable knowledge with the general public from one of the foremost authorities on the many worlds interpretation of quantum mechanics. We've only done minimal editing on it, hence it's 26 minutes long. But to help you out, here's a chart of where Sean Carroll answers certain questions. So in case you want to skip right to that part, you can do so. This chart will also be in the description below. I think I'm like most people, and I'm a big skeptic of the many worlds interpretation, but Sean Carroll was kind enough to indulge me on answering some of the toughest questions about it. You'll see that I was quite starstruck by Sean Carroll, who's one of my favorite physicists, and I pretty much forgot all the questions that I was going to ask him, but I think I remembered, fortunately, the big ones. So enjoy, my friends. Hello.
Hello.
Can you hear me, see me?
I can hear you and see you, yes. How about you?
I can do that as well. Thank you.
Good.
Fantastic. Sure. I can't tell you how excited I am because I've been listening to your lectures and your teaching company videos for years. So it's a real pleasure. Thank you for taking the time. Yeah. How are you doing? How are things? How are you making out?
Yeah, all things considered, right?
Yeah. I see you've been making videos on your YouTube channel.
Been making videos, yes, that's right. Learning slowly how to do this. It's not my expertise, but I'm trying to get better at it.
Well, if I can help you, or my team can help you at any time, let me know. We can make some graphics and stuff like that. So what I wanted to do is I kind of just give you a little bit background what I'm trying to do here. Many worlds is getting very popular, and I think that's largely due to you because you've been promoting this, and people take you very seriously. They consider you highly credible, of course. So I think you've single-handedly popularized this idea. I'm a skeptic. I am like Bob in chapter 8, and I presume you're Alice. And what I want to do in this video is present the merits and the good and bad points of the Copenhagen interpretation, as well as the good and bad points of the many worlds interpretation. Those two only, not any of the other interpretations. And sort of present that as fairly as possible. I felt like I could not present many worlds very fairly because of my internal bias and my visceral dislike of the science behind it. And I'm hoping that maybe you can shed some light, or maybe there are no answers, and we just kind of have to, continue in our search to find the answers. It seems to me you're replacing the mystery of the collapse of the wave function, which is mysterious in Copenhagen interpretation, with the mystery of the branching in the many worlds interpretation. So can you talk about how the branching is less mysterious than the collapse would be?
Sure. I think that it's really no contest, to be perfectly honest. The problem with Copenhagen is that it is manifestly an incomplete theory. Nobody can possibly think it's the final answer. You say, when you observe a quantum system, its wave function collapses. And if you ask, well, when do you observe? What counts as an observation? What about one atom bumping into it? Does that count as an observation? And also, what is the underlying reality that is happening? What is the real true mechanism that is going on beneath the surface? Copenhagen just says, we don't know. That's not our job. We're not going to answer those questions, okay? We know it when we see it, wave functions collapsing. Whereas many worlds is 100% completely specified. There's an equation, the Schrodinger equation, and that's it. There's nothing that deviates from the Schrodinger equation at any time. So there's no mystery about when branching happens in the Everett interpretation. You have the Schrodinger equation describing the behavior of physical systems, and those physical systems interact with each other, and they branch, which is to say there is an environment, there is a set of things out there in the world that we don't keep track of. All the photons, all the molecules of air in your room, you might know some coarse features of them, but you don't know the position and velocity of every molecule or every photon, right? Mm-hmm. So you don't keep track of that. And therefore, when a quantum system becomes entangled with that environment, that's when branching happens. And we can quantify it. We can tell you how quickly it happens. We can tell you when it happens. There's no loose ends there anymore.
Where is the branching in the Schrodinger equation?
Well, if you believe many worlds, everything that exists dynamically is the Schrodinger equation. There are no other equations.
Mm-hmm.
So it's not that the branching is in the Schrodinger equation. It's that when you put certain kinds of initial conditions into the Schrodinger equation and let it evolve, branching happens, whether you like it or not. So let's think about it this way.
Mm-hmm.
Let's imagine you're measuring the spin of an electron. Okay, this is a classic example for quantum mechanical measurement. And you have some apparatus. We don't need to go into details about what the apparatus is, but the apparatus has the following properties. If the electron is spin up, which means it's spinning clockwise according to some axis that you've chosen, then the apparatus will always measure that the spin is up. In other words, your apparatus is accurate. It doesn't make mistakes in that way. And if the electron is spin down, then your apparatus will always say it is spin down. Okay? Those are the requirements, that you haven't made a mistake when you built your apparatus. Then, the principles of quantum mechanics, the Schrodinger equation in particular, says without any doubt that when you measure an electron that is in a superposition of spin up and spin down, your apparatus goes into a superposition of having measured spin up and having measured spin down. Again, that no one disagrees with that. That is just a clear prediction of the equation. If you also understand that your apparatus is a big macroscopic thing that is constantly interacting with the environment around it, all these photons, all these particles of light, etc., then it will become entangled with the world around it, and that's when the branching happens. So it's not quite that you can say the Schrodinger equation leads to branching. The Schrodinger equation, when applied to the appropriate physical situation, predicts that branching happens.
Presumably, there is still a probability that I will find myself in one branch versus another. Is that the case with the Schrodinger equation?
No.
I mean, is that the case with the many worlds? Because okay. Can you talk about
the right thing to say, many worlds, and this is legitimately difficult, but it's not difficult because of the theory. It's difficult because our experience in the world is just not up to the task of conceptualizing this, okay? Yeah. What the theory says is when you measure something and the world branches, what was one person, you, is now two people. You in one branch and you in the other branch. And there's no such thing as which of those two people your older self has become. Your older self has become both of them. But those two people are now separate. They live in different worlds. They can't interact. They don't know about each other. They don't, have any resonance spiritually with each other or anything like that. There's two separate people. So the vocabulary to use in many worlds is, we know what will happen because it's a deterministic theory. We know that one you will evolve into multiple yous. All of those multiple yous will experience slightly different things. And what we can do is, when those multiple yous are first come into existence on these different branches, we can say, what probability should they assign to being on one branch or the other, given that they don't yet know which branch they're on? And that's where the probability comes from in many worlds. It's not that there's a probability of something happening. It's the probability of where you are in the wave function of the universe.
Okay. So the Born rule would not apply? Would the Born
rule 100% applies.
To many worlds.
The vocabulary you attach to it is different. And again, this is nothing weird or special in quantum mechanics. This is an old debate about the nature of probability. You say, well, I know that when I flip a coin, there's a 50-50 probability that it will come up heads, okay? That's a traditional thing you might say. But if you dig deeper into what that means, what do you mean by that exactly? One way of saying it is there's something truly unpredictable about the universe, and we just don't know whether the coin's going to become heads or tails. But there's another way of saying it, which is, well, if you knew every position and every velocity for the atoms in your thumb and the coin and the air and so forth, we could predict. There's a deterministic answer about what will happen. We just don't know those things. So the probability still is there, but it's not the probability of true randomness in the universe. It's the probability of our ignorance of what is happening in the universe. That's a sort of Bayesian notion of probability that has become very, very popular just among philosophers and scientists who work with probability generally.
Okay.
And that's what many worlds takes advantage of. Many worlds says the probability, the Born rule, the statement that the probability of seeing an outcome is given by the wave function squared, doesn't come from intrinsic randomness in the universe. It comes from the fact that when you branch, you don't know which branch you're on. There's ignorance there, and the right Bayesian thing to do is to assign a probability to being on any one branch given by its wave function squared, the Born rule.
Energy conservation. It feels like, where could all the energy come from for these new worlds? Now, in one of your interviews, I saw that you mentioned that we can't really think of it in terms of new energy being created, but rather the energy of the Schrodinger equation being fractionalized into new worlds as they're created.
That's right.
So two questions around that. I think I'll quote you. You said each world gets a little bit thinner, although its inhabitants can't tell. So what does it mean when you say that a world gets thinner?
So there's two things going on. I think that this is again, this is not like a question you ask because you don't get it. This is an important question that we need to sort of think about what it means. It's a legitimately difficult question that is new to the many worlds way of looking at things. In many worlds, there's two different things you might mean by the energy of the universe. Okay. One is the energy of all the branches of the wave function, okay, like all the worlds at once. That has an energy. The other thing is what the energy of each individual branch looks like from inside, okay, to the perspective of the people inside each branch. What is the energy? And these are two things. They're different things, but they're related to each other. And the relationship is not that you take the branches, the energy of each branch from the interior point of view and add them. Okay. That's not what it is. Sorry, that's just not what the math says. What the math says is take the energy from inside each world that the observers in that world would say, weight it by the wave function squared, right? Every branch of the wave function comes with an amplitude, a number. This is where the probability comes from, right? That amplitude squares the probability that you find yourself on that branch. The energy equation works exactly the same way as the probability being on one of the branches somewhere is always going to add up to 1. The energy of the universe that you get by adding the energies of the individual universes weighted by their amplitude squared will always add up to the energy of the total universe. So the total universe with all the branches has an energy which is 100% conserved. The energy within any one branch almost looks like it's conserved. It's not quite exactly conserved because there's quantum fluctuations, but it's pretty close to being conserved. So when you branch the universe in two, the energy that you perceive in your universe doesn't decrease by half. It stays almost exactly the same.
When you say the universe, I presume what you're meaning is the multiverse of the many worlds?
Well, when I say the wave function of the universe, I mean a collection of all the branches. That's what you might want to call the multiverse. I don't call it the multiverse because cosmologists use the word multiverse for something else.
Yes.
But the collection of all the branches, right.
Talking about the multiverse, how does the many worlds relate to the multiverse of, string theory? Would each multiverse of string theory have its own many worlds branches?
Yeah, they're completely independent, roughly speaking. Mm-hmm. So I think it's the other way around. The branches are more fundamental in some way. Mm-hmm. Every branch describes what you and I would call a universe. And if that universe actually is multiple universes strung together, as they are in string theory, then every branch has multiple pocket universes strung throughout space.
Oh, okay.
Space exists in the branches. The branches don't exist in space.
I find myself on one branch. You find yourself in one branch.
The version of you on this branch finds itself on one branch. There's other people who descended from the same past you. They're on other branches.
I'm going to get into this question of consciousness. Why is it that I experience just this branch? I'm conscious of this branch. I am not conscious of the other branches. What you're saying, I think, is that my other versions are saying
other branches.
I'm sorry, say that again.
There are other people who are conscious of those other branches.
And they're asking the same question. Why am I?
Something close to it. Look, it's almost exactly like identical twins, which at one point were the same single cell fertilized egg, okay? But rather than just duplicating its cells and becoming one person, it split into two different people. Nobody says those identical twins are two copies of the same person. That would be a weird thing to say. They're different people, right? When the branching happens, there are now two different people. They had the same past, but they're different people now.
Okay. And it's an innumerable number because of...
We don't know how big it is, but it's a very, very big number. It could be finite but super duper big, or it could actually be infinitely big, yeah.
In your book, you mentioned 2 to the 10 to the 122, I believe. And
that's one of the numbers it's bandied around, yeah.
And I like that number because I think it comes from, as you said, the maximum entropy that our universe could have.
Right.
Right. Okay. Can you conceive of any kind of test, akin to the Bell's inequality that could confirm or repudiate many worlds?
Yeah, absolutely. I mean, many worlds just says the Schrodinger equation is always true. All you have to do is do an experiment where the Schrodinger equation is manifestly violated, and you're done. You falsified many worlds.
But if you falsify Schrodinger equation, if you falsify Schrodinger equation, it would basically repudiate all interpretations because everything is based.
No, actually, there are interpretations of quantum mechanics. The word interpretations is not a good one here.
Okay.
There are formulations of quantum mechanics where the Schrodinger equation is only sometimes true. Other times there are objective collapses of the wave function. Roger Penrose's version of quantum mechanics has this property. There's a theory called GRW where the collapses just happen randomly. Okay. These are different ways of getting quantum mechanics, the same empirical predictions to the experiments we've made so far, but different predictions for experiments we're still trying to do.
Is many worlds something that you had always been attracted to from the very beginning, or has your viewpoint of the interpretation evolved? Were you a Copenhagen promoter in the past?
Yeah, I would say I was never really a Copenhagen promoter to the extent like most students of quantum mechanics, I didn't think about it, right? When I first learned quantum mechanics, I was trying to solve differential equations for boundary problems and reflection coefficients and perturbations of the hydrogen atom. You don't worry too much about the interpretations or the foundations. By the time I was in graduate school, I started thinking about quantum gravity and quantum cosmology a little bit, and almost everyone who does quantum gravity or quantum cosmology is a many worlds person. Once you start thinking about the wave function of the universe, many worlds is a very natural place to land. So I believe many worlds to the extent that it seemed to be a good fit to understanding quantum gravity and so forth, but I didn't really think deeply about the different formulations of quantum mechanics until the last 5 or 10 years or so.
Why is it getting so popular?
I mean, to be fair, there is a sophisticated modern descendant of the Copenhagen interpretation. There's an approach called epistemic formulations of quantum mechanics, where basically you take the attitude that the formalism of quantum mechanics is a tool to predict the probability of experimental outcomes. It is not a reflection directly of the underlying reality. So I am not very sympathetic to that approach because my goal is to understand the underlying reality.
Completely agree.
Modern epistemic approaches just don't want to do that, and so therefore I'm not that interested in them. But there are also other realist versions of quantum mechanics other than many worlds. There are hidden variable theories, there's these spontaneous collapse theories, etc. So of all these theories, there's zero question that many worlds has the simplest formulation, the simplest set of postulates, the simplest set of ingredients. The only question is, does it fit the data, right? Do the predictions of this super duper simple set of postulates actually account for the world that we experience? That's a good question. That's, that's something that people are still trying to understand. But I think that as we improve our understanding of physics and our technological abilities to probe different regimes of physics, it becomes less and less okay to fudge the quantum mechanicalness of reality with the Copenhagen interpretation. We need to take the foundations of quantum mechanics more seriously. And if you're someone who works in fundamental physics, cosmology, gravity, field theory, many worlds just a very simple natural fit, and all of the other attempts just look kind of like a kludgy mess. And so it's not much of a competition within that particular subfield.
Gotcha. I was intrigued by, I believe your current area of research has to do with entropic, kind of an entropic interpretation of the nature of the universe. Is that correct? Is that your current area of research?
Well, it has to do with emergent space-time from quantum mechanics, and entropy plays a big role in understanding why the way that space-time emerges gives rise to things like gravity and the curvature of space-time that Einstein talked about. Yeah.
So how is that going? Are you writing papers on this? Can we expect something? Is there any insight that you can give us about what you think is the true, whether this is true, that the emergence of space and time perhaps comes from entropy?
Well, I think that, again, I don't want to say entropy. It doesn't come from entropy. It comes from quantum mechanics and entanglement. Entropy is a tool that we use along the way to get there.
So you don't believe entropy? You don't believe entropy is fundamental?
Depends. I don't know what you mean by fundamental, to be honest, right? I wouldn't put entropy front and center of our way of doing things. It's important, but I think it gives the wrong impression if you say comes from entropy or something like that. It's a little more subtle than that. I just don't want to give people the wrong idea.
Right.
I think it's more accurate to say that in our point of view, space-time comes from entanglement, from quantum entanglement. I think that's a more direct notion. But I think it's very promising, but it's also very, very young and ill-formed. In our most recent paper, which was a couple of years ago, we wrote out a very long list of assumptions and tried to make the claim that if all these assumptions are true, we get the result we want. And therefore, there's a research program, go through these assumptions one by one and show whether or not they're true. And that's what we're trying to do. There are more papers coming out. So far so good, but there's huge obstacles, and there's easy to imagine ways that the whole program could fail. So I'm not, pushing it prematurely. I'm just saying it's a really interesting way to try to imagine going forward.
I appreciate your time. Is there any question that I've missed here, that you commonly hear, that you want to kind of address?
I think you got the big ones. Energy conservation is a big one. I'm still working on how to best address that one. But yeah, there's lots of questions, but I think you hit the major ones because you read my book. You know what the major ones are.
Right, exactly. You got to read the book, guys. You got to read the book. Now, is there? Are you working on a book currently, Sean, that you can tell us about?
I'm going to, nothing anywhere close to being finished, but one of the things I'm going to do is actually to write an undergraduate textbook on quantum mechanics. Nice. So not to proselytize my favorite interpretation, but certainly to take the idea seriously that the fundamentals of quantum mechanics matter, in particular entanglement and open systems, not just solving the same differential equations over and over again, really taking the deep part of quantum mechanics at face value.
I see. Okay. Fantastic. Can't wait. Again, I appreciate your time. Thank you so much. And what I'd like to do is, after I'm done with the video, I'd like to send it to you. It's going to be about a 10 or 15 minute video max, 15 minutes maximum. And I'd like to send it to you because I don't want to misrepresent anything that you're saying. Now, the way that we're going to design this video is, as you're talking and talking about these concepts, we're going to put some animations and graphics to visualize the kinds of things that you just said. You know.
Okay.
So
cool.
It's this visualization that I'm not 100% certain how it should be done. So I'm hoping that you can give us some feedback on that. One question I do want to ask you is there any way to visually represent decoherence? You know, this is critical to understanding many worlds. How do we explain that? How do we explain decoherence? I mean, collapse is kind of easy to understand, but you know, the difference between collapse and decoherence. How should we put that graphically?
I mean, you got me. You just sort of need to draw multiple copies of the world, which are slightly different, right? Like the photons in one world are in slightly different places than in the other one. You know, the closest that I can come is the following. If you really believe in, let's imagine your setup really is, you've measured something like the spin of an electron, and you have a meter that says, you know, I haven't measured it yet. It was spin up or it was spin down. Okay, so there's literally a dial and an arrow pointer. Okay, they can go to spin up or spin down. And if you imagine that the background of the dial is white and the pointer is black, then you can show that, you know, you can draw a picture of a photon that hits the dial, and if the arrow is pointing one direction, the photon is absorbed by the hand, right, by the pointer. And if the pointer is pointing in the other direction, the photon bounces off the dial. So because the dial, the pointer is in a different position, the environment is now different, right? There's an entanglement that immediately and viscerally happens between the position of the pointer and all the photons around it. And that's decoherence, basically.
Okay. All right. I'm going to have to...
there might be a figure like that in the book somewhere.
Okay, I don't remember that, but I'll check. All right, that's great. I will replay this video and try to get that straight. But I'll send it to you to see if you know, to see if we have it right. I've never actually seen that anywhere. Okay, what am I looking at? Ah, okay. What page is that on?
Bottom of page 118.
Okay.
That's the best I can do.
118. I'll note that down. Okay, yes, I think I do vaguely remember seeing that. Okay. Excellent. Thank you so much again, Sean, and I'll be in touch via email, and really look forward to your future work. And you've been an inspiration to many, and our viewers are going to be super excited to see this.
Good. Can't wait for it. Let me know.
All right. Take care, my friend.
Okay. Bye-bye.